You're watching Shitoku Tech Storytime Best of Dark Matter, Dark Energy, and Black Holes.
This is a little difficult for me to get my head around. I still haven't come to grips with dark matter in a sense that I can understand it, but apparently the Hubble telescope can detect small clumps of what they call cold dark matter. They're using the gravity of galaxies to magnify quasars in other galaxies, and then they can essentially trap a view of dark matter in this lensing effect. Pretty complex stuff. You might want to check it out.
You're going to have to strap on your thinking cap for this one. Scientists shed light on the mystery of dark matter. Dark matter is composed of particles that do not absorb, reflect, or emit light. We suspect there's dark matter because of the interaction of gravity with visible objects. So we know there's more to the universe than what we're actually seeing. So they put forth this candidate, a particle they recently discovered called the D-star hexaquark. It's composed of 6 quarks. Quarks are the fundamental particles that usually combine in trios to make up protons and neutrons that we're familiar with as parts of atoms. The 6 quarks in a D-star result in a boson particle, which means they can combine in very different ways to the familiar protons and neutrons. Shortly after the Big Bang, not the TV show, but the actual Big Bang that formed the universe, D-star hexaquarks could have grouped together and cooled and expanded to form the 5th state of matter, the Bose-Einstein Condensate. Wow, this is definitely a mouthful here. It's worth a read. Maybe read through it a couple of times. So previously on Shitoku Tech News of the Week, I've spoken about the Bose-Einstein Condensate, and this article caught my interest. Are black holes actually dark energy stars? Anyway, there's this Event Horizon telescope that has been peering at Sagittarius A for the last several years, looking at the center of the Milky Way galaxy. And most astronomers expect to find a black hole. And the black hole has the telltale signs of a bright swirl of light produced by a disk of gases trapped in the black hole's orbit surrounding a black shadow at the center, the event horizon. This encloses the region of space where the black hole's singularity's gravitational pull is too strong for light to escape. But a Lawrence Livermore National Observatory physicist, George Chaplin, says he doesn't expect to see a black hole at all. He says they're not real. He believes that what we'll actually find is a dark energy star. This dark energy permeates the entire universe. It expands the fabric of space-time itself, and even gravity. Chaplin believes the immense energies in a collapsing star causes this condensed phase of space-time. Without a singularity in space-time, there is no black hole. So far, his theories haven't taken hold. Chaplin and other physicists modeled space-time as the Bose-Einstein Condensate, a state of matter that arises when taking extremely low-density gas to extremely low temperatures near absolute zero. This is quantum mechanics, and general relativity emerges as a consequence of the way that space-time condensate behaves on large scales. Chaplin goes on to explain that he expects this dark energy star to actually appear much like a torus or a donut shape, hollow in the center. A similar effect was observed when quantum mechanics is used to model rotating drops of superfluid. There too, a central vortex can form in the center of a rotating drop and surprisingly change its shape from a sphere to a torus. Yes, go ahead and read this article and your brain will definitely get bigger. Look for the link in the description below. If you're a fan of Shitoku Tech News of the Week, and it's now
Shotoku Tech Saturday Story Time. You know I'm all excited about dark matter and the Bose-Einstein Condensate. Well, I've actually just created this fifth state of matter on board the International Space Station. I know Astro Christine has already returned, but here she is installing the Cold Atom Laboratory on the International Space Station. I think this took place in 2018. So this is a suitcase-sized device, and it can chill atoms of rubidium and potassium in a vacuum chamber, and then they use a laser light to slow the movement, and then magnetic fields contain the resulting cloud of atoms, and it is cooled to nearly absolute zero at minus 273 degrees centigrade, and this creates the Bose-Einstein Condensate. So this was originally theorized by Albert Einstein and Satyendra Nath Bose in the early 20s as the fifth state of matter. The other four states are solids, liquids, gases, and plasma. This supercooled gas no longer behaves as individual atoms and particles, but rather as an entity in a single quantum state. Wow, mind blown, and we're just getting started. Okay, astronomers believe they have observed the light of 1 trillion suns due to the merging of black holes. When black holes collide, the ensuing cosmic drama was assumed to play out under the black cloak of darkness, given that both objects are already invisible. But now they believe they've made the first optical observation of such a merger, marked by a blaze of light 1 trillion times brighter than the sun. They spotted this gravitational wave at this LIGO Observatory. There was ripples sent through the fabric of space, and the latest observations suggest that when these cataclysmic events occur within the accretion disk of an even more gigantic black hole, they are brilliantly illuminated by the surrounding dust and gas, making them also visible to optical telescopes. So this supermassive black hole has been fine for years, and then all of a sudden they observed this more abrupt flare. So they think this flare was likely the result of a black hole merger. Okay, so this is a deep story here. The corona of supermassive black holes may be the hidden source of mysterious cosmic neutrinos seen on Earth. So let's talk about what neutrinos are. They're subatomic particles so tiny that their mass is nearly zero, and they rarely interact with other matter. Now, high-energy cosmic neutrinos are created by energetic cosmic ray accelerators in the universe, which may be extreme astrophysical objects such as black holes or neutron stars. They may be accompanied by other electromagnetic waves and gamma rays at lower energies, and even sometimes gravitational waves. But this interesting, it's called Ice Cube Neutrino Observatory, and the detector is buried deep in the Antarctic ice. And they're perplexed by the observation of neutrinos at this Antarctic observatory. And they especially find that at this particular instance, they're not accompanied by these other wavelengths that they would expect to see. We know that sources of high-energy neutrinos must also create gamma rays. So the question is, where are these missing gamma rays? See, so they're not seeing the gamma rays and they're getting these neutrino rays. So their theory is supermassive black hole systems are the source of these neutrinos. So Planet 9 may be a black hole the size of a baseball. When you're observing these TNOs or trans-Neptunian objects, we know there's some gravitational influence at the very edge of our solar system. But this optical gravitational lensing experiment, or OGLE, may explain how Planet 9 is actually made up. Gravitational microlensing occurs when a massive foreground object, such as a black hole, passes directly in front of a background object, such as a star. This acts as a lens, distorting and amplifying the light from the object behind it. So we've got 5 years of these OGLE observations, and there's 6 strange microlensing events that seem to have occurred when objects roughly 1/2 to 20 times the mass of the Earth have acted as gravitational lenses. These could correspond to black holes up to 26,000 light years away. Or they could be a free-floating planet at the edge of our solar system, or perhaps even a baseball-sized black hole, herding these TNOs in a predictable orbital pattern.
A team of scientists from the University of California, Riverside have precisely measured the amount of matter and dark energy in the entire universe. The team determined that matter makes up 31% of the total amount of matter and energy. And as we see in this diagram, that total amount of matter, 20% is regular matter, that which we can observe, stars, galaxies, dust, and gas, and the remaining 80% is dark matter. And that dark matter and regular matter combined equal 31% of the total amount of matter and energy in the universe. The remainder is dark energy. We talked about that in our time travel articles recently. If all the matter in the universe were spread evenly across space, it would correspond to an average mass density equal to only about 6 hydrogen atoms per cubic meter. So you'd need 4 times that amount of dark matter to represent our universe. So most of our universe consists of a type of matter which we don't yet understand. These observations were made by looking at member galaxies in galaxy clusters, and by determining the orbits of these member galaxies in these galaxy clusters and comparing them against simulations, they were able to determine the total amount of matter in the universe. This was such an accurate method that they were able to determine the mass of each cluster individually, rather than rely on indirect statistical methods. Their findings are also supported by other observation techniques such as cosmic microwave anisotropies, baryon acoustic oscillations, type 1a supernova, or gravitational lensing.
Spaghettification might sound tasty, but if you're a star near a black hole, it actually means death. So a rare blast of light emitted by a star is sucked in by a supermassive black hole was spotted by scientists using telescopes around the world. This is a tidal disruption event, and it's the closest flare of its kind, occurring just 215 million light years away. This is what happens when a star gets too close to a black hole. The black hole shreds the star into thin streams of material, a process called spaghettification. Tidal disruptions are rare events, and they're not always easy to study because, the universe is big and there's a lot of dust clouds and stuff like that. But they were able to catch this particular event and view it in extreme detail. So they used several different telescopes and a satellite to view this flare named AT2019QIZ over a 6-month period as it grew brighter and then faded away. So this sounds like science fiction, but this tidal disruption event actually happens, and they were able to see it in complete detail. When a black hole devours a star, it can launch a powerful blast of material outwards that obstructs our view. This happens because the energy released as the black hole eats up stellar material propels the star's debris outwards. So in this particular case, they were able to identify what was happening early enough to observe the whole process. Several sky surveys discovered this emission, and they were able to determine which ground telescopes would be best suited for the observation. This star was roughly the same mass as our sun. Dust and debris is being drawn up as the black hole launched a powerful outflow of material with velocities up to 10,000 kilometers per second. Well, that's quite a dust storm. This study in the Astrophysical Journal says that the universe is getting hotter. It's increased by 10 times over the last 10 billion years and reached about 2 million Kelvin today. So this is based on a theory of how large-scale structure forms the universe. Now this large-scale structure refers to patterns of galaxies and galaxy clusters on scales just beyond individual galaxies. And it's formed by the gravitational collapse of dark matter and gas. So as the universe evolves, gravity pulls dark matter and gas in space together into galaxies and clusters of galaxies. And this drag is violent, and it releases gas that is shocked and heated up. So this has shown the scientists how to clock the progress of cosmic structure formation and check the temperature of the universe. Thank you for watching Shotoku Tech Saturday Storytime. I invite you to click on the link down below in the description to check out the Blogspot article with the links to all of these stories. And I really want you to take a look at this blog because I've gone back through and added an article for every single video from the Shotoku Tech Saturday Storytime episodes all the way back to December 21st. So this blog is fully searchable, so if you wanted to look up stories about the moon or Mars or exoplanets, then you could see all of the stories that I've covered on those topics. And I think it's going to become even more interesting as time goes on. So thank you and have a great week. Thank you for watching Shotoku Tech. Please subscribe, comment, like, and share.